Well, good morning. I am Berardi Sensale Rodriguez from the University of Utah, and today I'm going to talk about graphene as a material for basically optical and terahertz devices. Okay, this is an outline of this talk. I'm going to start with an introduction where we're going to see what is this material and what are its optoelectronic properties. Then we're going to look at several device applications that people have been proposing over the last 2 or 3 years. And finally, I'm going to end up this talk with some short conclusions. Okay, so basically here I copied from Wikipedia what is graphene, but I don't want anybody to read it. It's like, this is just a guide. Okay, graphene is a two-dimensional semiconductor which is composed of carbon atoms. These atoms are arranged in an hexagonal lattice, as I show here. Okay, so a very important characteristic of this material is that it's two-dimensional. It's just an atom thick. One can see that because of this, when we look at reciprocal space, the structure of graphene is also hexagonal, and at the edges of the first brilliant zone, graphene has a linear EK dispersion. That this is different from traditional semiconductors, where this kind of relation is parabolic. Also, graphene does not have band gap. Valence and conduction band touch into a point that is called the Dirac point. So these are some characteristics of graphene that come from its 2D nature. Okay, and one can see that these characteristics lead to some unique properties. One of them is that because of the linear EK dispersion, carriers, both types of carriers, have zero effective mass, so they are massless. This means in practice that we can achieve very high electron mobility for both types of carriers, electrons and holes. Okay, and because of the symmetry of the structure, all the properties are symmetric between electrons and holes. Because of this, graphene has been the subject of a lot of attention in electronics. For instance, high-frequency transistors. There have been reports of devices achieving FT, intrinsic FT above 300 gigahertz. And also, it has been the subject of a lot of attention for kind of flexible electronics, because you can take graphene, you can transfer in any arbitrary substrate, and you can make a device. We can make graphene devices almost everywhere. So let's look a little bit to its optoelectronic properties. And for this, here I am showing the band diagram of graphene under two bias conditions, okay, which are represented by different Fermi levels. Fermi level tell us basically the energy up to where electronic levels are filled. Okay, so these shaded regions represent occupied electronic states. If we shine light, electrons can absorb it, and they can jump to a higher energy free electronic states. When those transitions happen from band to band, for instance, valence to conduction band, they are called interband transitions. And whenever they happen inside a band, for instance, as shown here in red, inside the valence band, they are called intraband transitions. So when we look at the electromagnetic spectrum and we look at different regions, one can see that the behavior of this material changes. For instance, when we look at the terahertz range, these are wavelengths in the orders of hundreds of microns. The terahertz photon energy is very tiny, just a few millielectron volts. So the energy normally required for an interband transition is in the order of hundreds of millielectron volts. So what happens is that if we are kind of normally far from the Dirac point, interband transitions are not significant, and the terahertz optical conductivity is only ruled by the contribution of intraband transitions. And one can see that at these frequencies, the optical conductivity follows a Drude-like relation, no? And this has been seen, for instance, with terahertz and infrared spectroscopy in graphene samples. This is some work from Kono's group from Rice University showing the Drude-like behavior of graphene at these frequencies. In contrast, if we go, for instance, to the visible range, one can see that the properties of graphene dramatically change. Now, optical phenomena is basically dominated by interband transitions, okay, and the conductivity can be found to be the optical absorption can be found to be a constant in graphene, which is 2.3% per graphene layer, and this have been demonstrated, for instance, by Haim's group from Manchester. So basically, if we summarize, if we look at all the electromagnetic spectrum, we see this. In the visible range, the optical conductivity of graphene is a universal constant, independent of Fermi level. In the terahertz range, it heavily depends on Fermi level, therefore can be tuned, okay, and basically is ruled by intraband transitions. And in the infrared range, we have contributions from both inter and intraband transitions, and also we have some tunability. And one can see, for instance, in the terahertz range, no, that as we become closer to the Dirac point, the density of states available for intraband transitions, the number of electrons who can absorb energy and jump to a higher empty electronic state decreases. No? Therefore, the optical conductivity decreases. And basically, people have shown the tunability of optical conductivity in all these frequency regions. This is a work from Basov's group in UC San Diego, where they show tunability of optical conductivity in infrared. And this is some work that I did when I was a grad student in my advisor's group, which basically shows the tunability in the terahertz range. So why or why not one would like to use graphene for making optoelectronic devices? Well, we are engineers, and this is a semiconductor. So it offers tunable optical and electronic properties. Therefore, we can make active devices. What are the advantages of these materials? First, we can integrate it with arbitrary substrate. We can make, as I told you, graphene devices almost everywhere. Second, it offers high-frequency electronic properties, for instance, electron mobility, that are comparable to those of the best traditional semiconductors, if not superior. This is like an example. The best mobility reported in graphene, this is graphene transferring to boron nitride, is around 100,000 centimeters square per volt second, okay? And this is a room temperature, which is a value much higher than that in any other semiconductor. Then what we have is that this material offers low cost of fabrication, which together with these integration possibilities, I think that is of interest for industry, no? And finally, this is a 2D material. The two-dimensional nature gives us the ultimate quantum confinement. We have electrons confined just to a single atomic layer, and this is an atomic layer, for instance, without dangling bonds, which also translates into better electronic properties. And what are the disadvantages of graphene? Basically, in the world, there are not such things as completely flat surfaces, and when we transfer graphene, normally we get defects, impurities, we have problems, and this translates into having a finite minimum conductivity. Graphene is a material that we actually cannot be turned into like an insulator state. So this has been basically one of the reasons why people is no longer kind of looking at this material kind of for transistor logic and applications like that. And the other big problem is that it is difficult to achieve uniform material properties over large areas. And this is a problem of the transfer process of this material. So let me go into some applications now that we know the material and we know some of its properties. The first one that I want to mention, this is a work from a group from Professor Shang here in University of Berkeley, who show electroabsorption optical modulator based on graphene. The idea here is the following. We have a silicon-rich waveguide where the mode is confined here. Okay? Here, basically, we have silicon, aluminum oxide, and graphene. Okay? So this is kind of a FET-like structure. By applying voltage between the silicon and graphene, here there are two contacts, one can basically tune the Fermi level in graphene. And the idea is the following. For a given wavelength, okay, only electrons from this state, they're shown here kind of in blue, up to here, can jump into here, okay? So basically, and this is because momentum and energy have to be conserved. No? Basically, if the Fermi level is above this this blue line, okay, light can be absorbed. Here we have occupied electrons who can jump here. So the material here has minimum kind of transmission. However, if the Fermi level drops below the blue line, now these electronic states are empty, okay, and we don't have any optical transition, and the transmission goes too high. And now, in the other case, if the Fermi level goes above the top blue line, okay, electronic levels here are filled, here are also filled, so we also don't have any optical transitions, and the material basically, again, becomes transparent. So this can operate as an electroabsorption modulator, and people have seen that the response goes up to 1 gigahertz, and this is limited by the parasitic RC kind of constants in these devices. So a challenge is how to improve parasitics, especially in the ungated regions of this device. The same group demonstrated a modulator where now there are two layers of graphene, one gating each other, and here what happens is that you can get kind of twice the absorption per unit length. So this is a way in which to improve the performance. I would like to comment also in a similar idea that Professor Campani mentioned, like in his presentation, that is basically by having graphene in top of silicon waveguides, one can make phase shifters, okay? And in this device proposal, they basically show that they can get 360 degrees phase shift with only a voltage scar shown, not the voltage that is applied, of 0.12 volts. So that can be another promising application. In terms of optical modulators, I want to mention this. We have been looking so far in the previous slides to devices where the kind of optical beam goes in the plane of the graphene. If one shines light kind of normal to the plane of the graphene, now one can still modulate, for instance, in this case, the optical reflection. This is a structure that is graphene oxide metal, okay? So light is shined this way, and we look at the reflected light. And what happens is that we can tune the absorption between 0 and 2.3%. Light passes 2 times, so we can get around 4% modulation of the reflected light in this device. The performance is not as good, but this is a device that basically is like the absorption happens just in an atomic layer. Basically, as I told you, the same kind of devices can be engineered in the terahertz range. This is an example of an electroabsorption modulator. And we have observed, this is from my advisor group, that you can achieve around 16% modulation depth. And in this case, the performance is limited by the quality of graphene. you can do the same in reflection, okay, and improve the performance. You can get 4 times more modulation by cleverly engineering the cavity in this case. And basically, you can take these concepts together with metamaterials to further improve the performance. Here, these are metamaterials, for instance, where operating as modulators, they can achieve enhanced modulation depth. I like to mention this other device that we have recently been proposing, that is an active filter. Basically, it's a metamaterial whereby tuning the conductivity in graphene, okay, one can change the resonance of a filter, okay. Basically, these are kind of resonators, split ring resonators, which can be open or short in some gaps, okay. And basically, this is like another idea that is having waveguides, okay, whereby applying some voltage in the graphene, we can change the optical path, therefore also make phase shifters, okay, and by having arrays of this, one can make beam steering. So, yeah, it's like, I'm going to skip this slide about basically some active devices and end up this talk with these conclusions. Basically, graphene is a two-dimensional semiconductor. Because of being two-dimensional, it allows us for unlimited degree of integration and superior properties. Also, because of being a semiconductor, we can tune its properties, so we can engineer multiple device applications. So, thanks for your attention.
Any questions for the speaker? So, how do you see the evolution of this device, for example? What is the modulation bandwidth you can achieve?
In these things, it's like I think that, for instance, in Jose's case, he was looking things like you can potentially achieve like 50 gigahertz or things like that, I think, that I remember. But, okay, those are like theory.